Welcome back, students. In this video segment, we will cover one section, section 16.4, Green's theorem. So we'll start with a question. Is there a connection between line integrals and double integrals? And I wouldn't ask the question unless it was yes. So yes, there definitely is. So I'll elaborate a little bit here. It's called Green's theorem. Okay, so Green's theorem starts with a curve C. So some of the terminology in this description of the curve C is real important to talk about or to concentrate on, and some of it isn't. So C we start out with is a positively oriented curve. That means it's oriented counterclockwise. And it's also what's called piecewise smooth, which essentially means that there aren't too many, and we'll leave the word too many undefined. There aren't too many jagged edges. There could be some jagged edges, but not too many, with too many left undefined. And the last thing is that it's simple closed. That means it doesn't cross itself. It's not like, for example, of figure 8, and the number 8 is not simple closed. It crosses itself. So C might look something like this. Okay, it's got to be closed, so I got to close it up. It's positively oriented, so it's oriented clockwise. And your author has a really nice. It's a traditional way of describing, besides using the word counterclockwise, a traditional way of describing a positively oriented curve is that if you were walking along the curve in the direction of its orientation, the interior of the closed curve would be on your left. Okay, so if you're walking along the curve and to your left is the interior of the curve or of the closed curve, then it's oriented positively. Okay, so let D be the region inside. So D is the region inside of the curve. C is the positively oriented, which means counterclockwise oriented curve. And here's Green's theorem. Green's theorem says then that the line integral along C of p of xy dx plus q of xy dy, a real common integral for us, equals the strange looking double integral of the partial of q with respect to x minus the partial of p with respect to y. Okay, that's kind of an interesting thing. Now here's a quick something for you to notice, just to get used to looking at Green's theorem. Suppose that the integral was the result of computing the work due to a force whose components are P and Q, of course in the xy plane. Suppose that the force was conservative. So what would this line integral give? It's kind of a good review of line integrals of conservative forces and stuff. So it would be 0. But remember, the test for the function being conservative was that the partial of q with respect to y equals the partial of the partial of p with respect to y equals the partial of q with respect to x. And look at that difference in the integral sign. Look at that difference right there. That would be 0. So this is the Green's theorem we can use right away to show that a really quick proof to show that the integral would be 0, because if the force were conservative, the integrand on the right hand side would be 0, and the double integral of 0 would be 0, and that's going to equal the line integral, so the work would be 0. If you miss that, don't worry about it. The most important thing right now is Green's theorem itself, the integral relationship that I've highlighted in red. Okay, where C is a positively oriented curve and D simple curve, a simple closed curve, and D is the interior of the region of this closed curve. Okay. Now, before we look at some examples with Green's theorem, there's a symbol that's often used as a special symbol for the line integral portion of this. We may write for the line integral symbol, the integral sign, the curve C, and with a little circle written around the center of the integral. This little circle indicates a couple of things. It integrates, no kidding. It indicates that the curve is closed and then it's positively oriented. Okay, so we only put that little circle along the middle of the integral sign to indicate, or if the curve satisfies the conditions necessary for Green's theorem, if it's a positively oriented closed curve. Very often you'll also see a little arrow inside of the circle. I'll try to draw it in there. A little tiny arrow in there. Okay, so Green's theorem can be written as the integral, little circle. Ooh, yeah. I could write it a little better. Little circle. I won't put the little arrow on it. See, this means integral, the closed curve, positively oriented, P dx plus Q dy. I'm leaving the of xy notation out just to make it a little easier on our eyes. Equals the double integral over the interior of the partial of q with respect to x minus the partial of p with respect to y dA. Okay, so let's take a look at some examples here. This section should be pretty short. There's not a lot to do in this section. So let's take a look at some examples here. All right, so for example, I want to evaluate the integral along a curve C, but the curve C is closed and positively oriented, so there's our symbol, of x minus y dx plus x dy, where C is the unit circle, centered at the origin, centered at 0, 0. Okay, but remember it's implied here, and just by writing that integral sign with a little circle around the middle of it, that it's a positively oriented unit circle. Okay, so let's do this two ways. Let's do this by direct computation. Direct computation of line integrals is not always recommended. We saw that in the previous section when we were integrating conservative functions or vector fields. Let me spell computation here. That it's not always the best idea just to start parameterizing your curve and evaluating the line integral. The same goes here in the use of Green's theorem. So by direct computation, well, how do we evaluate a line integral? We stuff a formula for the curve into the integral and evaluate it as a Riemann integral, just a regular integral from Calc 1. So the unit circle, let's parameterize the unit circle in the easiest way possible. X equals cosine t, y equals sine of t. We've seen this parameterization over and over and over and over again. Okay, so if x equals cosine t and y equals sine t, then what's dx? Dx equals negative sine t dt, and what does dy equal? Cosine t dt. So let's do this integral. The integral along the curve C in the positively oriented direction of x minus y dx plus xy, or no, not xy, x dy equals the integral. Well, to get around the circle, we go from 0 to 2 pi. T goes from 0 to 2 pi. And it's x minus y, so x is cosine t, y is sine t, there's x minus y. Dx is negative sine of t dt. dt. There's the first part of the integral. Plus, we're still under the integral sign, plus x dy. So x is cosine of t, dy is cosine of t dt. So let's simplify this. Let's factor out the dt and do even some more. So we're looking at, if we distribute the negative sine of t in the first part of the integral, we get negative cosine t times sine of t, and then plus sine squared t. And from the second part of the integral, we get plus cosine squared t. And of course, sine squared t plus cosine squared t is 1. So we're just looking at the integral from 0 to 2 pi, negative cosine of t times sine of t, plus 1 dt. Okay. The first part of the integral, real easy to evaluate. You let u equal cosine of t. Then du is negative sine of t dt. So du is just right there. It's right in the integral sign. So it's just u du, and the integral of u du is 1/2 u squared. So it's 1/2 u cosine squared t. And you can always stop the video and verify this. And then the integral of 1, antiderivative 1 is t, most general antiderivative, t plus a constant, or just t, since we're looking at a definite integral. Now at 2 pi and at 0, the cosine are equal. So cosine squared are equal. They're both equal to 1. When we subtract those, we get 0. So the only thing we're going to get is 2 pi when we substitute t equals 2 pi. Again, cosine squared of 2 pi is 1. Cosine squared of 0 is 1. So those subtract out. So the value of this integral is 2 pi. This wasn't bad. This could have been much worse if the line integral was more complicated. So now let's use Green's theorem. So now, by Green's theorem, Green's theorem. Let's do it. So, by Green's theorem, here, let me write Green's theorem right above here. Green's theorem, just to get used to it, says integral p dx plus q dy equals the double integral over the interior of the region of partial q partial x minus partial p and partial y dA. Okay, so our integral looks like the integral along c x minus y dx. I think it was x minus y. Yeah, and plus x dy. Plus x dy. So the p in this case is x minus y. The q is x. So Green's theorem says that this integral becomes the double integral over the interior of this unit circle, because remember we're integrating along the unit circle, of partial q partial x. Well, if q equals x, partial q partial x is 1. Minus partial p partial y. Well, if p equals x minus y, the partial derivative of p with respect to y is -1. So remember, you have to be careful. We're subtracting, and the formula for Green's theorem subtracts, and so we're subtracting -1. So this is nothing more than the double integral of 2 dA. Now, this is something what's going to happen here is something that happens frequently with physics. At least I noticed it when I was taking physics a million years ago. Is look at the double integral. It's the double integral. It's 2 times the double integral over d of 1 dA. That's just the area of the region. This is 2 times the area of d. There's no integration needs to happen here. No actual use of the fundamental theorem of calculus here. So the area of d is just the area of a unit circle. It's pi r squared, pi times 1 squared. all I used was area equals pi r squared, where r equals 1. Okay, so we get 2 pi. Okay, oops. Let me draw a little better. That's good. That's good. 2 pi. Okay, so that's how Green's theorem works. Now in this case, for this particular example, it wasn't that much simpler to use Green's theorem than it was to use the just to compute the line integral directly. It was simplified a little in that we didn't have to actually evaluate a double integral. But I want to look at a little bit more of an extreme case. Okay, so here's our next example. Let's evaluate the integral along the curve C oriented in a positive direction, that's what that symbol means, of the square root of 1 plus x cubed dx plus 2xy dy. Okay, what's missing? Well, C. I haven't described it yet. So where C is the triangle pictured. And I'm going to go off camera to draw this for you, so I'll be back in about 2 seconds. So here's our curve C. Okay, a curve C is definitely oriented in a positive direction, a counterclockwise direction. Okay, now let's do this. Let's attempt to do this again the 2 ways. So by direct computation. And see what happens. Well, in order to do this, we got some work to do. We should divide this curve up into little segments of curves, line segments, in fact. So C1, C2, C3. So C is the union of these curves. Well, let's parameterize these curves. These curves are little line segments. Now I'm going to use again something that I hope you've been using in homework, and that's a formula for the line segment. R equals R naught plus T times R1 minus R naught. And your author uses a slightly different form of the same formula. He distributes the T and regroups stuff a little differently, but it's the same formula. So this is a formula for a line segment we use real often in this course. Right about now, for T between 0 and 1. So let's take a look at C1. C1, we can view R naught being the origin plus T times R1 can be viewed as the vector 1, 0 or I, so it's 1, 0 minus 0, 0 or T times 1, 0. So there's our vector form of line. So the parametric form of a line would be x equals, just looking at the components, x equals T, y equals 0, where T ranges between 0 and 1. So this is just the beginning. Here's the parameterization of C1. C2, for C2, the initial R value can be thought of as the point, or not the point, but the vector 1, 0. So here's R naught plus, well, if R naught is 1, 0, then R1 should be 1, 3. See, this is the point 1, 3 up here, so it can be regarded as a position vector whose components are 1 and 3. So plus the vector whose components are, I'll put this one in. This one's T times, if you will, 1, 3 minus 1, 0, or the vector whose components are 1, 0 plus T times, let's see, 1 minus 1 is 0, 3 minus 0 is 3, T times 0, 3. So if I break this up into components, I'm going to get x equals 1 plus 0t, and y equals 3t. Again, t ranges between 0 and 1. Of course, I have to do the same thing with C3. So C3 is R equals, the initial R value, R naught is 1, 3. And R1 is the origin, and R naught is, let's see, let me get this right. Oh yeah, R naught is 1, 3. So the origin as a vector, 0, 0 minus 1, 3 is plus t times negative 1, negative 3. Okay, again, you can stop the video and verify this if you need. So this is 1 minus t for x and 3 minus 3t for y, where of course t varies between 0 and 1 in all three cases. Okay, and we haven't even started to evaluate the integral yet. Okay, so let's do the direct computation of the integral along C closed curve oriented positive direction of the square root of 1 plus x cubed dx plus 2xy. 2xy, oops, let's see if I can clean that up a little bit. 2xy dy. Okay, so this actually becomes the integral along C1 plus the integral along C2 plus the integral along C3. Okay, of the same integrand, dx, the dx plus dy, pdx plus qdy business. Okay, so let's look along C1. Along C1, it becomes the integral from 0 to 1. We stuff the parameterization of C1 into the integral, so the square root of 1 plus x equals t, so dx equals dt, plus 2 times x times y, 2 times t times 0, times, well, if y equals 0, dy equals 0 dt. Okay, plus, and I'm not even going to bother with C2 and C3, the integral along C2 dot 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 plus the integral along C3 dot dot dot, and I'll show you why. And I realized when I wrote this integral I forgot to cube t. So look back at the integral from 0 to 1. It's 1 plus t cubed. So this is the integral from 0 to 1 of the square root of 1 plus t cubed dt plus the other integrals along the other portions. And the only reason I'm not evaluating those integrals or putting them in is we aren't able to go any further anyway. The first integral is impossible to evaluate. This is impossible to evaluate. Impossible to evaluate. We don't have enough math in this course, enough background material to prove this. This integral is an example of what's called an elliptic integral, and they're nasty in a sense that first, in a sense that they cannot be evaluated by using the fundamental theorem. There is no elementary antiderivative for the square root of 1 plus t cubed. Okay, so that's a problem. Well, if we want to evaluate this line integral. So let's see what happens with Green's theorem. Okay, so now by Green's theorem, let's do that. So now by Green's theorem. So Green's theorem says, I'll write Green's theorem out one more time just so we get used to seeing it. The integral along a closed curve oriented positively of p dx plus q dy is the same thing as the double integral of partial q partial x minus partial p partial y dA. Okay, so where's our integral? The integral along C closed curve, positive oriented direction, 1 plus x cubed dx plus 2xy dy. Now, this is going to equal the double integral over the interior of our region. So the interior region is inside this triangle. So over the interior of the region, d of partial q partial x, the partial with respect to x of 2xy. That's a q. There's a big old q right there. Okay. Minus the partial of p with respect to y. Partial with respect to y of the square root of 1 plus x cubed. Now that's nice. Why is that nice? What's the partial with respect to y of a function of x? That is real nice. What's p? Okay, dA. That is really sweet. So this becomes the integral over d. Partial with respect to x of 2xy is nothing more than 2y. And partial with respect to y of square root of 1 plus x cubed is 0. 2y dA. Oh my goodness, that's really super simple. The integrand is super simple, and the region is super simple. There's the triangular region. Okay. I'm going to move our region down for us. Give me a second. So there's our region off to the left there. Look at that simple region. This can be interpreted as a type 1 region, type 2 region, either one. Let's interpret this as a type Roman numeral 1 region. Function on top. Function on top. There's the function on top. It's just a line. What's the equation of that line? Y equals what? It goes through the point 0, 0, and 1, 3. Well, if it goes through 0, 0, it has a y-intercept of 0. If it goes through the point 1, 3, that means if x equals 1, y equals 3. So it has a slope of 3. That's super simple. Okay, so this becomes the integral, iterated integral, interpreting it as a type 2, so a type 1 region rather. We're going to integrate first with respect to y, as y goes from 0 to the line, and then we'll integrate with respect to x as x goes from 0 to 1. And we'll do this. This is just the integral from 0 to 1, antiderivative of 2y, y squared, from, let's see, this y varies from 0 to 3x, and then integrate that with respect to x. Look at how simple that integral is. As opposed to doing this directly where it's impossible to evaluate, I would say this is a pretty simple integral. This is 3x squared dx, or 9x squared. 0 to 1, 9x squared dx. So antiderivative of 9x squared, 3x cubed, from 0 to 1. Oh my goodness, look at how simple this is. This is 3. That's wild. So Green's theorem not only makes it easier, it makes it the ultimate easier. It makes it from impossible to extremely simple double integral. Okay, so when you consider your homework and definitely your exams, be careful with these with the evaluation of these line integrals, both with respect to using Green's theorem and not even using Green's theorem. If this were a line integral of a conservative vector field, then it may be a really good idea to use the fact that the vector field is conservative and use the fundamental theorem of calculus for line integrals after constructing a potential function to simplify the integral. And in this case, in the case of Green's theorem, don't rule out Green's theorem and necessarily evaluate the line integrals directly. Green's theorem can be used to evaluate line integrals by converting them to double integrals, where the double integrals can be much easier to evaluate. Okay, Okay, so what I think I'll do is one more example, and then we'll call it quits. Okay, so let's do that. Let me take a second to write out our example for us. I'll be right back. Okay, so here's our example. Evaluate the integral, the line integral. Notice there's no little circle along the center of the integral symbol. So this is not it's not fit for Green's theorem, this integral. Okay, so evaluate the line integral of f dot dr. So it looks like a work integral where f equals the force whose components are e to the negative x plus y squared, and the second component e to the minus y plus x squared. And c consists of the arc of cosine. I drew this below for us. The arc of cosine from negative pi over 2 to pi over 2. So here's negative pi over 2 along the x-axis. Here's positive pi over 2 along the x-axis. Here's, of course, 1. So along the arc of cosine from negative pi over 2 to pi over 2. So this is definitely in the negative direction. We're going clockwise. And then the line segment from pi over 2, 0 on the right to negative pi over 2, 0 on the left. So this is a negatively oriented curve. Okay, so Green's theorem cannot be applied directly here. All right, so let's try to do this. Well, let's try to use Green's theorem anyway. Well, how can we do this if we can't use Green's theorem? Why can we try it anyway? Well, okay, so the integral along C of f dot dr is force the integral to be an integral in the positive direction. How do we do that? Well, this is equal to, we have a formula for doing that, the opposite of the integral in the opposite direction of f dot dr. This is an integral. Ooh, yeah, my little circle there is terrible. This is the integral in the positive direction. Okay, if C is negatively oriented, the opposite of C is positively oriented, and the formula then says the integral along C is the opposite of the integral along negative C. So now we can use Green's theorem. Okay, just for emphasis here. Just for emphasis. Green's theorem. I don't know why I have this in red. That's all right. It requires positive oriented curve. And the opposite of C is positive oriented if C itself is negatively oriented. Okay, so we're set to use Green's theorem on this. Okay, so this equals the opposite of the integral along negative C, which is the integral along a closed curve in the positive direction, of p dx. Well, p was e to the minus x plus y squared dx plus q dy. I'm just taking that dot product of f dot dr now and writing the integral in scalar terms. So q is e to the minus y plus x squared dy. Okay, and let's invoke Green's theorem here. So Green's theorem says negative is just going to follow. This becomes the integral along the interior of the region. We'll call that d. And C was the negatively oriented curve. So the interior of d of the partial of q with respect to x. So the partial of e to the minus y plus x squared with respect to x. It's going to wipe out the exponential portion. I think I have this right. Yeah. Minus the partial with let me clean up my partial symbol here. The partial with respect to y of p e to the minus x plus y squared dA. Okay, so now let's perform these partials. So the partial with respect to x of e to the minus y is 0, of x squared is 2x. Partial with respect to y of e to the minus x is 0, and the partial with respect to y of y squared is 2y dA. Now look at that. That integral is not that difficult to evaluate. Okay, we can interpret this as a type Roman numeral 1 region. Okay, so we can now rewrite this as an iterated integral of, let's see, type Roman numeral 1, we're going from y equals 0 to y equals cosine x. Okay, and let's see, this we're still going to be integrating 2x minus 2y in this iterated integral dy, and then dx from minus pi over 2 to pi over 2. This integral is not so bad. You could evaluate it. Well, let's just keep going. Okay, so this is negative integral, negative pi over 2 to positive pi over 2. Integral of 2x with respect to y is 2xy. The integral of 2y with respect to y is y squared. As y goes from 0 to cosine x, and then integrate that with respect to x. So let's keep going. That's pi over 2 to pi over 2. Let's see, y is cosine x, so 2x cosine x minus cosine squared x. And at 0, we get 0. So this takes us right into Calc 2 territory. Now the first integral is real simple. We could integrate it by parts. That can be done too. You can integrate this directly. But I'm going to use something here to help us out. The function 2x times cosine x, that is an odd function. It's symmetric with respect to the origin. Why? Because cosine x is even, symmetric with respect to y-axis. And 2x is odd. It's an even times an odd function is an odd function. And the integral of an odd function, from negative a to positive a, regardless of what a is, of an odd function, dx is 0. The integral of an odd function, I'm trying to draw a real quick odd function, from negative a to positive a is clearly 0. Integral from negative a to 0, you get the opposite of the area. From 0 to a, you get the area itself. So the integral cancels out. Okay, if you don't see that, that's okay. It just means you have to integrate 2x cosine x by parts. So what we're left with is the integral from negative pi over 2 to pi over 2 of cosine squared x. Okay, now the integral, cosine squared x is even, so we don't get such a luxury. We could use, there's a formula for simplifying the even functions a little bit, but I'll avoid it. So let's integrate it from negative pi over 2 to pi over 2. Way back in Calc 2, we integrated powers of sines and cosines. So if the powers of sines and cosines are even, then we use power reducing formulas. 1 plus cosine of 2x. Feel free to stop the video, review that if you need, but make sure you can do it, because these integrals require us to be able to integrate. So, all right, to find antiderivatives. So the integral of 1 is x, integral of cosine of 2x is 1/2 sine 2x. Okay, and this is carried between negative pi over 2 and pi over 2. Okay, so the sine of 2x at pi over 2 is sine of pi, which is 0. And the sine of 2x at negative pi over 2 is the sine of negative pi, which is also 0. So we don't get any contribution at all from the sine term here. However, we do get a contribution at x. At pi over 2, we get pi over 2. And at negative pi over 2, we get negative pi over 2. And we subtract those things with the fundamental theorem. Pi over 2 plus pi over 2 is pi. So we get half pi. Okay, so the value of this integral is pi over 2. Again, using Green's theorem. We converted the line integral, or work integral in this case, because it was f dot dr. It looks like a work integral. We converted it to a double integral. Okay, and that ends section 16.4. So go ahead and dig into homework when you can on this, okay, as soon as you can. And I'm looking forward to talking with you all again very soon.